questions 8 through 10 on the 2013 grade 12 Euclid math contest. Determine all pairs AB of positive integers for which a to the power of 3 plus 2ab is 2013. A to the power of 3 plus 2ab is equal to 2013. Factor out an a, we get a squared plus 2b is equal to 2013. Now you say, where do I go from here? Well, this times this is 2013, so it's probably helpful to break up 2013 into its prime factors, and those are 3 times 11 times 61. So this times this is 3 times 11 times 61. So I've got a, and I've got a squared plus 2b. Those are my two, factors on the left side. So let's think about what kind of combinations. Obviously, since they're all positive integers, a has got to be less than this guy, a squared plus 2b. So what are my possible combinations? I can have 1 for a in 2013 for a squared plus 2b. Or I could have 3 for a and 11 times 61 for the other guy. Or I can have 11 for a and 3 times 61 for that guy. Or how about 61 and 3 times 11? But this last one doesn't work because remember a has to be less than a squared plus 2b, and this is 61 and this is 33. So that one, I put a little x beside it that it doesn't work. So I really only need to be concerned with the first 3. All right, let's do it. Let's look at the first one. If a is 1, then what's b? Well, that's going to give you this scenario, that a squared plus 2b is 2013, right? So a is 1, so substitute that in. We get 1 plus 2b is 2013. So 2b is equal to 2012, and therefore b is equal to 1006. So that's my first pair. AB is 1006. All right, so that takes care of that one. Now let's look at the next one. When a is 3, and this is now equal to 11 times 61. So we have a squared plus 2b is equal to 11 times 61. A is 3, so substitute that in. That's going to be 9 plus 2b is equal to 11 times 61, which is 671. So that means 2b is equal to 662, and therefore b is equal to 331. So now I've got another one. AB is 3331. So that takes care of that one. Now let's check out the last one, which is this one right here. A squared plus 2b is equal to 3 times 61. Well, a is 11, so that means 121 plus 2b is equal to 3 times 61, which is what, 183? So that means 2b is equal to 62, and therefore b is 31. So there we go. I've got the last one. AB is 11 and 31. So these are my ordered pairs, and those are the only ones. So there we go. That's the answer. Determine all real values of x for which the log of 2 to the x minus 1 plus 3 to the x plus 1 base 2 is equal to 2x minus the log of 3x to the base 2. Log of 2x minus 1 plus 3x plus 1 all to the base 2 is equal to 2x minus the log of 3x to the base 2. Okay. Well, I think it's good to put everything on one side except this 2x. Put all the logs on one side, so that will help. What we can do is we can use one of the log rules to combine them. So plus the log of 3 to the power of x. Now the log rules allow me to combine these guys. It becomes the log of 2, base 2, but then I can combine them as 2x minus 1 plus 3x plus 1. Multiply that by 3 to the power of x, like that. That is perfectly allowed by log rules. Now again, using log rules, this 2 to the power of 2x, that's the basic fundamentals of logs, is equal to this whole guy. So 2x minus 1 plus 3x plus 1 all to 3x multiplied by 3 to the power of x. Okay, let's see if we can simplify this a little bit more. What can we do here? Well, 2x squared, I can break up those like that. This is going to be 2x all over 2. This is going to be 3x times 3. And then this guy just remains 3x like that. And at this point, what I can do is make some substitutions. And the substitutions I will make are let 2 to the power of x equal a, and let 3 to the power of x equal b. Make it a little bit nicer for us. So it becomes a squared is equal to a over 2 plus 3b times b, like that. Okay, so as you can see, it's kind of pretty now. And let's see, let's move through this, multiply, and we get ab over 2 plus 3b squared. Multiply through by 2, and we get 2a squared is equal to ab plus 6b squared. Put everything on one side, and we get 2a squared minus ab minus 6b squared is equal to 0. At this point, we must factor. That is going to help us. And let's see what happens. This will be 2a, 3b, 2b, and then the signs plus minus. Yeah, that'll work out. That's basically just factoring that. So this helps me out tremendously. This tells me that either a is equal to 2b or 2a is equal to minus 3b. But this one is a problem because you can't take logs of negative numbers, right? So this is not going to work, the one that I just underlined. So the only one that's going to work is this one right here. So a is equal to 2b. Okay, let's go back and use these substitutions. A is equal to 2b, so that means if a is equal to 2b, that means that 2 to the power of x is equal to 2 times 3 to the power of x. Correct? Now we introduce logs back in, and let's just do it to base 10. Log of 2x, a log of 2 times 3x. So using log rules, I can bring the x out front, and then this one I have to break up first, log of 2 plus the log of 3 to the power of x. And then this becomes x log 2 is equal to log 2, and then bring the x out front, log 3. And then put x's on all one side. So x log 2 minus x log 3 is equal to log of 2. And then factor out the x. And you get the log of 2 minus the log of 3 is equal to the log of 2. And therefore x is going to be the log of 2 all over the log of 2 minus the log of 3. And that's it. So that's a very nice question about logarithms. Square WXYZ has side length 6 and is drawn, as shown, completely inside a larger square EFGH with side length 10, so that the squares do not touch and so that WX is parallel to EF. Prove that the sum of the areas of trapezoid EFXW and trapezoid GXZY does not depend on the position of WXYZ inside EFGH. They want us to prove that this sum, which is EFXW plus GHZY. So basically those are two trapezoids. The first one is obviously right here. this one right here. And the second one, GHZY, is this guy down there. And they want you to prove that the sum does not depend on the position of this square, meaning that square is currently obviously where it is, but if you moved it down to here, that sum would remain the same. If you move the square over here, that sum would be the same, and so on. Okay, let's work with this. First, we need to draw in some heights. So the first thing is going to draw in that height and this height right here. So the first one up top, I will label H1, and then this one down here I can call H2. Now, if you recall, if you have any sort of a trapezoid that looks obviously like something like this, right? The area is calculated as follows. If this is A, this is B, and this top to bottom is the height, the area of that trapezoid is A plus B over 2 times the height. So let's label what we can. We know that this big square has a side length of 10, and the small square has a side length of 6. All right, so let's figure out the areas now. So EFXW plus GHZY. The first one, it's going to be 6 plus 10 divided by 2 times H1. And the second one, also 6 plus 10 divided by 2 times H2. Now, so far, it looks like it's dependent on H1 and H2. We have to show that it's not dependent. All right, so how do we do that? Well, first, just simplify this. What's that? 8H1 plus 8H2. All right, so that's about as far as we can get with that. But on the side here, let's talk about H1 and H2. If you notice, if you draw a line all the way down, top to bottom, you'll notice that H1 plus the side of the square, which is 6, plus H2 is equal to the side of the big square, which is 10, right? So that means that H1 plus H2 is equal to 4. So if I isolate for 1, like H2 will be 4 minus H1, like that. So let's substitute this in. H1 I'll keep, and for H2 I'll substitute it to be 4 minus H1, which is what it is. So this becomes H1 times 8, 32 minus 8H1, and the 8 H1s cancel, and all I'm left with is 32. So basically what that means is that this sum is always going to be 32, regardless of what H1 is, and regardless of what H2 is. So it doesn't depend on those heights. So what you can do is just write one little sentence to explain that. So something like this should be sufficient. The area has a sum of 32. It's a constant sum. Therefore, the area is not dependent on the position of the square WXYZ and the corresponding values of H1 and H2. That should be good enough for number 9A. A large square ABCD is drawn with a second smaller square PQRS completely inside it so that the squares do not touch. Line segments AB, BQ, CR, and DS are drawn, dividing the region between the squares into 4 non-overlapping convex quadrilaterals as shown. If the sides of PQRS are not parallel to the sides of ABCD, prove that the sum of the areas of quadrilaterals APSD and BCRQ equals the sum of the areas of the quadrilaterals ABQP and CDSR. Our task in this question is to prove that APSD plus BCRQ is equal to ABQP plus CDSR. All right. So here we go. We're going to have to do a lot of labeling here, and this diagram is labeled in such a way to help us out. What we've done, first and foremost, is we took the original question, the diagram in the original question, and then we made this square around it. And then each of these areas we've labeled a letter to indicate its area, and there's a whole bunch of them, as you can see, a lot of areas, so each of those we'll talk about in the question. I also have to label a few things. The side length of AB I'll call x. So from here to here, I will call that x, that distance. And then the side length of the square that's in the middle on a slant like that, I will call that side length equal to y. So I'll just put 1y right there. And then I'm going to also label an angle, WPQ, and I'll call that theta. So WPQ is this angle right in here. So I'll just see if I can squeeze in a theta like that. And then similarly, all the other angles that are in those other smaller triangles are also going to be theta. XQR, YRS, and ZSP. So let's talk about these. XQR, where is that? XQR is this guy. That's also going to be theta. YRS is that one right there. That's also theta. And ZSP is this angle. That's also going to be theta. And as you can clearly see, that basically means that all those triangles are pretty much congruent and equal. So that means those triangles are WPQ is equal to triangle XQR is equal to triangle YRS is equal to triangle ZSP. And as you can see, they've already been labeled with certain areas. E for this guy, F for that one, G and H. And these are all equal. Those are all equal because they're congruent, they share the same side lengths, they share the same angles. Because in each of them they have a right angle, and each of them they have that theta angle. So the third angle will obviously be the same, and they also have the same side lengths. Each of them has a y. So there we go. This is the first established relationship. Now, for each of these distances, like QW, for example, which is right here, QW, from there to there, each of those distances are also similar. Well, I should say actually that they're the same. QW is the same as RX, is the same as SY, is the same as PZ. So this is QW, that's the same as RX, which is right here, is the same as SY, which is right here, is the same as PZ, which is right there. And if you use a little bit of trigonometry, you'll see that they're equal to y sine theta. That's the whole reason of putting in a theta in there. And also, if you look at other sides like WP, QX, YR, and ZS, so WP, these little guys now, WP, QX is this little guy, YR is this guy, and ZS is those. Those smaller sides are also all equal. And those are all equal to, again using a little bit of trigonometry, y cos theta. Now if you combine these, you'll notice something. For example, WP is right here, right? It's from here to here. But if you keep adding it to, say, PZ, from there to there, that will equal all the way the whole side, WZ. So those two, for example, combine to WZ. And they're equal. And similarly, if you do that for the other ones, for example, WQ is here, and then you add it to QX, that also equals the whole side. And that's also going to be equal, which is going to be the equivalent of WX. And similarly, if you add other components from here and here, they equal one full side length of that shape. So we get WX is equal to WZ, but we also get that equal to XY and ZY. XY is from here to here, and that's the equivalent of xr plus ry. So xr is right here, and ry is right here. And lastly, zy is from here to here, which is the equivalent of zs plus sy. So zs is here and sy is here. So when you add up all these guys, you get these results, and those all have to be equal because their sums are equal, because each of these was one of these and one of these. So now we got another establishment of equalities, and that basically proves that w, x, y, z, that shape, is a square, since all the side lengths are the same. And we'll call the side length equal to z. All right, we'll use that later. So we have established quite a bit here so far, but we still got a little bit more work to do. Now, the first thing we need to show, if we're trying to prove this guy right here, is that if you look at this diagram, we need to show the first thing is that a plus r plus c plus n is equal to b plus m plus d plus s. So let's explain this. A plus r, this is a, this is r. So if you add those two, it would basically be this portion of the shape. C plus n is this plus this. So if you add those two, it would be that portion. That is this part of the equation. Now we have to show that is equal to b plus m, which is this plus this, which would be that shape, and d plus s, which is this shape right here, this trapezoid. And when you do that, it will help us. So how are we going to do that? Well, the first thing we need to do is in ABXW, we need to have a height. So where's ABXW? ABXW is right here. We need to label a height. So I'll label a height top to bottom. Let's just call it from here to here. And we can call that K. Okay, so I'll put that there. And then, very similarly, for another trapezoid, ZYCD, which is down here, ZYCD, we also need a height. So let's put in a height, top to bottom, like that. And that one we'll call it L. So now we can figure out a little bit of a relationship. ABXW, if you were to look at it, ABXW is A plus R. So it's A plus R. But if you remember the formula that we had used previously, it's going to be this plus this divided by 2 times the height. So that's going to be x plus z. Remember, we had called that side length z from there to there. And then that's divided by 2 and then times the height, which we have called k. And then very similarly for ZYCD, that is going to be n plus c. And if we use the same formula, it's going to be x plus z over 2 times L this time, because that's the height. Now, notice a very interesting thing about these heights. If you go top to bottom like that, you'll notice that k plus this, which is z, plus L, all add up to one full side of the big square. And one full side of the big square is x. So basically what that means is that, note, k plus z plus L is equal to x. So that means k plus L is equal to x minus z. All right, so let's continue. on this side here. If we now add these guys, you will get a plus r plus c plus n, and that is equal to x plus z over 2 times k plus x plus z over 2 times L. Right? No tricks. Now we just factor out the x plus z over 2, and that will give me k plus L. And then x plus z over 2 times k plus L. But k plus L is x minus z, so I can substitute that in, x minus z. And then now this gives me 1/2 times x squared minus z squared. All right. Now at this point, x squared minus z squared is a very interesting finding. X squared represents the area of the big square, right? X times x. Z squared represents the area of that square. So x squared minus z squared is basically the area in between them. And the area in between them is essentially everything that I had talked about. All those guys. That's the interesting part. So the area in between is a plus r plus c plus n plus b plus m plus d plus s. And then therefore, if you multiply this 1/2 on this side, if you multiply through the equation by 2, you'll get 2a plus r plus 2c plus n is equal to, let's move this up, a plus r plus c plus n plus b plus m plus d plus s. That's what's remaining in the bracket. And then simplifying, you get a plus r, just one of them, c plus n, just one of them, is equal to b plus m plus d plus s. So there we go. We got a very, very helpful relationship as we had previously planned to. This one right here. Okay. Now we get to the final stage of the question where we have to find one more relationship, and then we can combine our results. So I'll keep that in the screen. Now the next thing we need to show is that r plus n is equal to m plus s. And I'll bring back that diagram. So here's r, and here is n. And we have to show those two have to add up to m plus s. So I guess those sort of corner ones. All right, so how are we going to do that? We're going to concentrate first on r, which is this guy right here. It's basically triangle QXB, that small guy, and that's r. Well, r, if we use the area of a triangle, it's 1/2 base. Base is QX. And height, if you remember, we had drawn a height top to bottom that was like that, and we had labeled that as k. So that's going to be the height, like that. And if you recall, r being equal to this, qx we had defined up here as y cos theta. So that's what I'm going to put in for the value of qx. So we have y cos theta, and then times k. All right. And then we want to do something similar to SZD, this triangle right here. Triangle SZD. Now that is labeled as n. Now that area, n, is also 1/2 base times height. The base is ZS. And then the height, if you remember, we had drawn a height top to bottom like that, and we had called that L. So that's going to be times L like that. And then recall that ZS, we had also given a similar value. ZS was also y cos theta. So put that in. N is equal to 1/2 y cos theta times L. And then when you combine these two, we have now r plus n is equal to 1/2 y cos theta times k plus 1/2 y cos theta times L. Now we can factor out 1/2 y cos theta, and when you do, you get k plus L. And then if you recall, k plus L was x minus z, so substitute that in, and you get y cos theta x minus z, and that's r plus n. Okay, so we can do the exact same thing on m and s, identical. We can draw, heights, and we can do the same comparison and have the same thing. So I'll just write that in. We can do the exact same analysis to show that m plus s is also equal to 1/2 y cos theta x minus z. So since that and that have the same value, we conclude that r plus n is equal to m plus s. And there is our next finding. So our first finding that was very important was this one. So we call this equation 1, and then this is our equation 2. And what we are going to do is combine them. So we are going to do 1 minus 2. And when you do that, I'll keep them in the screen. 1 minus 2, you are left with just a plus c is equal to b plus d. Where a, b, there's a, here's b, here is c, and here's d. So now we are in the final stage here. We want to prove in the end that ABSD plus BCRQ is equal to ABQP plus CDSR. Okay. Well, let's see. Let's see what we get here. Let's talk about the left side, and then let's talk about the right side. Well, the left side, ABSD, if we were to bring back that diagram, APSD, APSD right here. That one, in terms of the letters in the diagram, is D plus H plus N. And then this one, BCRQ, B is here, C, RQ. That one, in terms of our letters, is R plus B plus F. And then these ones here, I'll just write them out. It's A plus E plus S, and then C plus M plus G. Rearrange this a little bit. Put the B and D together. Put the R and N together. And then we've got these H and F. On this side, rearrange it a little bit. A plus C plus M plus S. And then E plus G. Okay. Well, look at this. B plus D is equal to A plus C up here, right? So that means this and this is equal, so that is fine. R plus N is equal to M plus S. So R plus N is equal to M plus S. And now we've got this H, F, E, G. Well, we had proven earlier in the question that all of those are equal way up here. That E was equal to F is equal to G is equal to H. So E was equal to F and G was equal to H. So there we go. That means that the left side is all equal to the right side, and we have now proven this relationship for number 9b. A multiplicative partition of a positive integer n greater than or equal to 2 is a way of writing n as a product of one or more integers, each greater than 1. Note that we consider a positive integer to be a multiplicative partition of itself. Also, the order of the factors in a partition does not matter. For example, 2 times 3 times 5 and 2 times 5 times 3 are considered to be the same partition of 30. For each positive integer n greater than or equal to 2, define p at n to be the number of multiplicative partitions of n. We also define p at 1 as 1, and note that p 40 is 7, since the multiplicative partitions of 40 are 40, 2 times 20, 4 times 10, 5 times 8, 2 times 2 times 10, 2 times 4 times 5, and 2 times 2 times 2 times 5. Determine the value of p 64. All right, so we draw a table and off we go. So we are now interested in p to the 64. So we're going to break it up into how many parts does it have? Does it have 1, 2, 3, 4, 5, or 6 parts? Well, the first one is pretty straightforward. If it has only one part, it would be just 64. If it has 2 parts, it would be something like either 2 times 32, or 4 times 16, or 8 times 8. 2 parts to it. 3 parts, 2 times 2 times 16, that would work. 2 times 4 times 8, and 4 times 4 times 4, that would also be a 3-part multiplicative partition. 4 parts, 2 times 2 times 2 times 8 for 64. 2 times 2 times 4 times 4, that's another way of doing it. 5 parts, there's only one way. 2 times 2 times 2 times 2 times a 4, and then 6 is all 2's. 2, 2, and 2. There we go. So we got to count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means P64 is equal to 11. So that takes care of part A. Part B, P1000. Okay, so obviously this is much, much more complicated. And I don't want to do it in this way because it's going to take a long time. But the thing is, even if it took a long time, that's not the real reason. The real reason is that P1000 gives us an opportunity to understand something about this question, that it doesn't really matter what the numbers are. The only thing that's important is the structure of the prime factorization. So I'll explain what I mean. P to the 1000, right? Well, 1000 is what? If you break it up into its prime factors, it's 2 to the power of 3 times 5 to the power of 3. So it essentially is of the form p to the power of 3 times q to the power of 3. So what I had said before, what I mean is the fact that it's 2 and 5 is not important. This is important. The structure of its prime factorization. What p is irrelevant, what q is irrelevant. But the fact that it's of the form p to the power of 3, q to the power of 3, that's what's important. Okay, so continuing in our tradition here, but in a slightly different way, we will now make our table. So we are looking at the number of parts that are divisible by p. The number of parts divisible by p and q. And then here I will put the multiplicative partitions, and here we will put how many of them are there. So first we'll start 1 and 1, and then we'll do 1 and 2, 1 and 3, then we'll do 2 and 1, 2 and 2, 2 and 3, and then finally 3 and 1, 3 and 2, and 3 and 3. All right, so let's go. The first one, where you have only a multiplicative partition where the parts are divisible by p once and divisible by q once. One such example is just p to the third q to the third, just the number itself. Another such example is when you break it up, p to the third times q to the third. So just to backtrack, the number of parts divisible by p is 1, and the number of parts divisible by q is 1. And that's this and this satisfy those conditions, and therefore I found 2 of them. Now let's go to the next one. The number of parts divisible by p is 1 again, but the number of parts divisible by q this time is 2. Such examples are p to the power of 3 times q squared. As you can see, the number of parts divisible by p is 1. There's only 1. But the number of parts divisible by q, there's 2 of them. And that's what I have to do. Another such partition is p to the power of 3q times q squared. And then another one is q times p to the power of 3 q to the power of 2. All right. So as you can see, I found 3 of these. Now, 1, 2 will give you the same sort of scenario as 2, 1. You just reverse the p's and the q's. So this is also going to be 3. All right. So that helps us out a little bit less work for us. Now let's go to the next one. The next one, to make the number of parts divisible by p is 1, and the number of parts divisible by q is 3 this time. I can make the following partitions: p to the power of 3 times q times q times q, or p to the power of 3q times q times q. And there's 2 of those. But 1, 3 is the same as 3, 1 in terms of its the way it occurs, because you just reverse the letters. So if there's 2 there, there's 2 here. All right. So let's go to the next one here, 2, 1. Hopefully by now you're getting a little bit of a hang of it. But 2, 1 I already did, so I can just assume that you'll be able to just flip the letters. Where there's a p, you put a q. Where there's a q, there's a p. Let's go to 2, 2 then. 2, 2. So this is going to be quite a few of them. We're going to have p times p squared times q squared. There's one of those. And then we have p squared q squared times p times q. And then we're going to have pq squared times p squared times q. And then p squared q times p times q squared. And then pq times p squared times q squared. And then we also have pq times p squared q squared, and then p squared q times pq squared. So we had 1, 2, 3, 4, 5, 6, 7 here. All right. So that took up a lot of space there. All right. So that belongs to this guy here. All of these. 2, 3. This next one. 2, 3 is going to have the following. We're going to have p times p squared times q times q times q. We're going to have p squared q times p times q times q. And then we're going to have 2 more, pq times p squared times q, and then pq times p squared q times q. So that gives me 4 for this guy, and that's going to be the same for 3, 2. And then the last one, which is down here, that's going to be, let's move this up a bit, p times p times p times q times q times q. That's one way. And then p times p times pq times q times q. And then P times PQ times PQ times Q, and then finally PQ times PQ times PQ. So this gives me 4. So now all I have to do is add up my sum. So it's the sum of these guys. So 2 3s, 17, 21, 23 plus 8 is 31. So P1000 is 31. All right. Now we move to part C. Determine with proof a sequence of integers a0, a1, a2, a3 with the property that p 4 times 5 to the m is equal to a0 p 2 to the m plus a1 p to the 2m minus 1 all the way to am p to the 2 to the power of 0 for every positive integer m. Well, p to the 4 times 5 to the m is what they've given us. And as if I have, I think, previously discussed, that the value of p depends on the structure of the prime factorization, not on the actual primes. So let me write that out. So the value of Pn depends only on the structure of the prime factorization of n, not on the actual prime numbers in the factorization. So we can put this in some sort of a structure and then just work with the structure rather than concentrating on the actual numbers. So we have 4 times 5 to the m, and that is what we have to figure out the p for. Well, that is 2 squared times 5 to the power of m, and this is equal to, if you were just to write them in terms of letters, p squared times q to the m, because remember, it doesn't matter what those numbers are. And we can use primes since only the structure is important. So we can use, say, p equal to 5, q equal to 2, and work with that. We can use any primes since only the structure is important, the structure of the prime factorization of n. So use p equals 5, q equals 2. And the reason we're using q equals 2 is because we need to prove an expression that involves powers of 2. If you notice, this involves powers of 2. So that's why I'm using 2. All right, so this we can now use 5 squared and then 2 to the m. And this is, of course, 25 times 2 to the m. All right, so at this point, we will now, very similar to before, make a table, and off we go. So here is our table. We have number of parts divisible by 5 on one side and number of parts divisible by 2. Now, the 5, there's only going to be 2 possibilities, either 1 and 2. But for the m, we've got quite a few. We've got m minus 1, m minus 2, and so on, right? M minus 3, dot, 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 and then eventually you're going to get to some sort of a intermediate point, m minus something, let's just call it s, and then you're going to continue, and then eventually you'll go all the way down to 1 and 0. So we have to now discuss this. What happens in this question is that when you are filling out this part, interestingly, the fact that you have these this situation where you are only worried about one part being divisible by 5, it actually doesn't change anything with regard to 2 to the m. So for example, this just is going to be p to the 2 to the m. This is just going to be p 2 to the m minus 1. And this is going to be p to the 2 to the m minus 2, like that. It actually doesn't have any effect since it's only one part. And you just fill this out all the way down, 2 to the m minus 3, and so on, dot, dot, dot. So when we get down here, it'll just be 2 to the m minus s, and then eventually p to the 2 to the 1, and then p to the 2, 0, like that. But when you get to this column here, then things start changing a bit. We have to now consider the fact that the number of parts divisible by 5 is 2. So now it's going to be a little bit different. Some of these earlier ones are not that different. It's just going to be 1. But then once we get to some of the ones that happen later, it'll be 2 times p to the 2m minus 2, and then 2 times p to the 2m minus 3, like that. Now we have to come up with a general term that we can put here for p 2 to the power of m minus s, but in particular when the number of parts divisible by 5 is 2. So for m minus s, when the number of parts divisible by 5 is 2, which is going to be this entry, the general formula is s plus 2 divided by 2. You take the integer value, that's what that symbol means, and you multiply it by 2 to the power of m minus s, the p of that. So that's what I'm going to put here. S plus 2 over 2, the integer value, times p at 2 to the m minus s. Okay? Dot, dot, dot. Now I have to figure out what is it when we have p to the 2 to the power of 1. My value now for m minus s is 1. And therefore m minus 1 is equal to s. So that's what I'm going to substitute right here. So substituting, we'll get m minus 1 plus 2 over 2, and that becomes m plus 1 over 2. And that is what you put here, m plus 1 over 2, the integer value. And the very last one, when you have p at 2 to the power of 0, now my m minus s is basically 0, so that means s is equal to m. So that's what I put here. And if I put m there, obviously it will be m plus 2 divided by 2. So this is my complete table. And now what I will do is I will combine them both. I will add this column to this column, then one next to it. So if I do, my very first one becomes 2 times p to the 2 at m. And then the next one, these guys will become again 2 times p to the 2m minus 1. And then the next one is 3 times p to the 2m minus 2. And then I've got one more, 3 times p to the 2m minus 3. And then I have got all these dot, dot, dots, and then we have a general term. And that general term, if I add this one to that one, will give me 1 plus s plus 2 divided by 2. And then that's all times p to the 2m minus s, like that. And then dot, 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 we get to the last two terms. And the last two terms will be 1 from this, and then add the m plus 1 over 2. So 1 plus m plus 1 over 2, like that, times p to the 2 to the 1, and then the very last one, of course, will be 1 plus m plus 2 over 2, the integer value, times p to the 2 to the 0. So, summarizing, a0 is 2, a1 is 2, as you can see, 2 and 2 there, a3 is equal to, a2 I should say, is equal to 3, this guy right here, a4 or a3 is equal to 3, and we have a general term, as, and that is equal to 1 plus s plus 2 divided by 2, the integer value. And this is the sequence that they are asking for in the question. And this is the official solution, part 1. And this is the official solution continued, part 2, which I'm including for you to further explain this very difficult question.